Hello guys, and welcome to today's video again, a continuation of what we started. So we are actually going to see the solution to the second problem in this particular video, that is determine the series solution of the equation d squared y dx squared plus x dy dx plus y equal to 0 by power series method. So let's dive into the solution, and if you are just watching this, we have already solved for this first one. I explained everything in full in details, and I laid some important background. So if you feel like you've not really watched this one, or if you're struggling with it, check the playlist so that you understand the solution to number one. So we are actually in number two, and in the next video we're going to tackle number three. So let's dive in. Okay, all right, so here we are now at problem 2, and there we go. So determine the series solution of the equation. So solution. Now I said that I'm going to introduce us to what I call Leibniz-Maclaurin method. Okay, Leibniz-Maclaurin method of analyzing solutions to differential equation. But before I do that, I would like to just give us a little test, just to test our hands a little on what the Leibniz-Maclaurin method look like. So I'm sure you might have actually studied it in class, and I'm just here to explain it under the assumption that perhaps you have an idea of actually what I'm talking about. Well, actually, the summary is that for Leibniz-Maclaurin method, if you have a function y is equal to let's say y equal to u v, if you want to differentiate it n times, okay, differentiating this function n times, y equal to u times v, so you either write yn or yn, okay, you write it like this, yn, but I'm going to be writing my own at the bottom. So yn is going to be what? So if you want to differentiate it n times, you're going to take the summation from, let me say, should I use n equal to 0 or z, n equal to, how am I using n? So r equal to 0 to n, okay? So you have your n combination r, n combination r, then you're not going to do, in this case, you will have un minus r. So un minus r is the un minus rth derivative, and vr is actually the r derivative. So I'm going to explain what this means. Okay, you don't need to, I'm not going to explain it by virtue of the formula, but I'm going to explain it practically. So let's just deviate a little. So assuming I give you a problem that's given that y is equal to x cubed, then exponential 2x, and I ask you to differentiate this thing n times, differentiate or find yn. That means you want to find the nth derivative of this particular stuff. If you want to find the nth derivative, the hint is to differentiate n times using the Leibniz-Maclaurin formula. So this is how we are going to go about it. Now, when you're differentiating a function n times, you must be careful the one that you choose as your u and the one that you choose as your v. Now, the one that you choose as your u should be the one that you can easily determine the n derivative of that function. Okay, whichever function that you're using as your u, it should be something that you can determine the nth derivative easily. So usually what we are going to be selecting as u is the likes of sine x, cos x, exponential x, natural logarithm of x, and so on and so forth, or even y itself in some cases, or y primes and y prime primes and y prime prime prime. So those are the ones we'll be selecting as u. But the one that we'll be selecting as v is the one whose derivative, okay, will actually reduce to 0. For instance, when you differentiate this one repeatedly, you discover that in the first time you differentiate it, it will be 3x squared, second time it will be 6x, and last time it will be 6, then the next time it will be 0. So the one that you should take as your v should be that function that in the course of differentiating it, it should actually approach 0. Then the one that you should take as your u, just like I said earlier, is the one whose nth derivative can be easily obtained. So let's differentiate this function n times. So follow me and see how I'm going to do. So yn, which is the nth derivative, this is sometimes written as y0. So the nth derivative is y0 plus n, which is still the same thing as yn, is equal to, first of all, my n combination 0. N combination 0 is always 1. So there will always be a 1 here, first of all. Okay, I hope you remember your combinatorial coefficients. Okay, your combinatorial coefficient. So I'm just going to write it down for us somewhere here. Now, n combination 0 is n, is 1, sorry. Now, n combination 1 is n. N combination 2 is n into n minus 1 over 2 factorial. N combination 3 is n into n minus 1 all over what? 3 factorial. Is that okay? And so on and so forth. Sorry, this is an n minus 1, then n minus 2. Sorry about that. The n combination 4 will be n minus 1, n minus 2, n minus 3 divided by 4 factorial. So these are our combinatorial coefficients that we should remember in the course of differentiating n times. So the coefficients of the first term that will result in this nth derivative will be the first combinatorial, which is what? 1. So you're now going to take your u, okay, exponential what? You're going to take your u and you're going to differentiate it n times. Okay, so to differentiate it n times, combinatorial coefficient first, then you're now going to take your function, which is u, and you differentiate it n times. And of course, if you can still remember, when you differentiate an exponential n times, you're going to get 2 raised to the power of n and exponential 2x. Okay, so this is what you're going to get when you differentiate an exponential function n times, because if you differentiate it once, you get 2 exponential what? 2x. Differentiating it 2 times, 2 raised to the power of 2 exponential what? 2x. 3 times will be 2 raised to the power of 3 exponential 2x, and so on and so forth. So n times will make this coefficient be raised to the power of n multiplied by exponential 2x. So gradually, first thing I did was my combinatorial coefficient, which is 1, and after putting my combinatorial coefficient, then I now took my u and I differentiated it n times. Then in my v, in the first term, I will not differentiate v, I'll leave it like this, x3. Okay, so I'm done with the first term. So the next term will now be the second combinatorial coefficient, which is n. Okay, so in the second combinatorial coefficient, taking n into account, I'm now going to differentiate my u n minus 1 times. In this first case, I differentiated it n times, but in the second term, it will reduce, the order of differentiation will reduce by 1. So instead of us to have n, we'll have what? 2 raised to the power of n minus 1 exponential 2x. Okay, so in reducing the differentiation of this one by 1, that means you differentiated n times here, you differentiated n times here, you differentiated 0 times here. But for v, this is your v and this is your u. Now in this case, you're differentiating your u n minus 1 times. That means you need to differentiate your v 1 times. So in all terms, if you add the number of times you differentiated u plus the number of times you differentiated v, it must amount to n. Okay, so that's the secret. If you add the number of times you differentiated u plus the number of times you differentiated v, it should be n. So n plus 0 is what? N. So if I differentiate my u n minus 1 times, I need to differentiate my v 1 times, so that n minus 1 plus 1 will now take me back to what? N. So differentiating this one once, which is my v over here, so this is my v and this is my u. So differentiating it once, you will give me 3x squared. So let me continue from down. So I have satisfied the second term. Okay, so it's just following this pattern. Your combinatorial coefficients, you differentiate your u n minus r times, and you differentiate your v r times. N minus r plus r is actually n. So all terms must have that property. Now that we have finished this term, we should go to the next term, and the next term needs a combinatorial coefficient, which is n of n minus 1 over 2. Okay, don't forget your combinatorial coefficient. Now that you have this combinatorial coefficient, now you now reduce the order of differentiation of your u. You differentiated n minus 1 times in this term, so you need to differentiate n minus 2 times. So it will just take the same pattern, which is 2n minus 2 exponential 2x. Okay, then you now, since you differentiated n minus 2 times, and you need to now differentiate this guy over here, differentiate him 2 times. So in differentiating this guy 2 times, you don't need to do it again because you've already differentiated 1 here. So when you differentiate this one again, it will now be what? 6x. So this is the second time that you're differentiating your v. Is that okay? Then let's go to another term. So another term will now have a combinatorial coefficient. That's my n combination 3, which is an n minus 1, n minus 2, all over what? 3 factorial. Then I'll now differentiate what? My u n minus 3 times. It will now be 2n minus 3. Are we good? Then exponential 2x. Then since I differentiated n minus 3 times, well, how many times do I need to differentiate v? 3 times, yes. But since you've differentiated 1, 2, if you want to get the third time, just differentiate this guy and you're going to get 6. So this is the third time, time that you're differentiating this guy v over here, meaning that if you differentiate x cubed 3 times, you get 6. Now immediately I get to this constant, there is no need for me to continue. Now that's the secret. Some of us will be wondering, if I'm differentiating n times, where am I going to stop? The place you're going to stop is where your v becomes a constant. When v becomes a constant, that's where you stop, because you know that when you differentiate it the next time, it's going to be 0. Is that okay? When you differentiate a constant the next time, it's going to be 0. So all other terms after this constant term is going to be 0. So this is where we stop. So the next thing for you to do is just to, look for what is common in this particular series. You understand? And if you're given this kind of problem in an exam scenario, I'll ask you to actually take the lowest term out. The lowest term is 2n minus 3. That's the lowest power of 2 is 2 to the n minus 3. So take the lowest power of 2 out. So you have your yn will now be equal to, if I factor out the lowest power of 2, which is 2 to the n minus 3, I can also see that all the terms have an exponential, what? 2x. So exponential 2x will now be equal to, in the bracket, so when you factor out 2 raised to the power of n minus 3 from 2 raised to the power of n, if you factor it out, you're going to be left with what? 2 raised to the power of 3 and x cubed. Is that okay? So the concept is that when you multiply this by this, you arrive at what? 2 raised to the power of n again. Are we together? So let's move on to the next one. And you now have plus. When you factor this 2 to the n minus 1, sorry, 2 to the n minus 3 from 2 to the n minus 1, take note of the difference, 3 and 1. So we're going to be left with what? Very good. 2 square, and you now have n, then dot 3 exponential what? Then 3x squared, like this. So this is your n, and the 2 square is coming from the fact that when you factor this from this, you're going to be left with this one. So if you do this times this, you're going to get this one back. Are we together? So let's move on. When you factor this from this term, cancels out, then take note of the power 3 and 2. So you're going to be left with 2. Okay, 2, then n minus 1 over 2, and we now have times what? 6x, and finally we now have plus. If you factor it out from the last term, it's going to leave you with n minus 1, n minus 2 over 3 factorial times 6. Everybody knows that 3 factorial is 6. So if we start doing some calculations, 6 and 3 factorial will cancel out. Our yn will be 2n minus 3 exponential 2x. Then you now have this times this is an 8x cube, then plus this times this is like a 12nx squared. Okay, 2 square 4 times 3, 12, and plus 2 cancelling out, 2 will have 6n minus 1. Then we'll now have plus n minus 1 n minus 2. So this is the solution to this particular problem. So I hope you understood it. So with this concept of differentiating n times, we are going to use it to what? Find the solution of this particular problem. Okay, so I want you to follow me gradually even as we delve into the solution of this problem. Okay, so now, given any differential equation of the form, let's see, we're given what's the question again? Try to remember. Okay, the squared y over dx squared, then plus you have x dy over dx, then plus y equal to 0. There are steps that you should follow, so I'll just write the steps here. So the steps is number 1, differentiate n times. That's to use power series methods to solve any differential equation like this. You differentiate n times. So the solution to this power series differential equations is usually evaluated at the point x equal to 0. Okay, we evaluate it at the point x equal to 0. So after differentiating n times, you now plug in x equal to 0. So you plug in x equal to 0 to the equation. So when you plug in x equal to 0 to the equation, you collect like terms and obtain recurrence relation. And this is just all you need. Okay, these 3 steps. So if you can get to your recurrence relation, I believe you've covered about 50% of your work. So follow me as we solve this problem together. Okay, so let's go. So we're going to differentiate n times. But I think there was something I skipped. Before you differentiate n times, it's usually good to convert this differential equation to a form that you can suitably work with. Now, the form I'll advise you to use is to use it like this. Convert your d2y dx squared to this form. Okay, convert it to this form. Let it be a y2. Okay, y subscript 2. Then this one will be x y subscript 1, and this one will be y0 equal to 0. Is that okay? So y subscript 2 for second derivative, then xy subscript 1 for first derivative, and y0 for 0th derivative, or the neutral function. You could write y0, or you could just write only y, depending on your choice, but I'll just write y0 so that we can get the gist. Okay, y0. Okay, so let me just leave it as y. So I'll leave it as y. So our y2 is second derivative, y1 is first derivative, and y is the 0th derivative. Now, the reason some people might actually write their own like this: y prime prime, then plus x y prime, and plus y. But this kind of method is not usually sweet. It's not usually convenient. Okay, so I'm going to discourage you from using this method. So don't do it like this. Convert it to subscript. So we are differentiating y2 plus x y1 and plus y n times. Okay, so let's go together. We'll start from the first term. Now, if we differentiate this term n times, remember it has already been differentiated 2 times. So when you differentiate n times, it will now be an extra, okay, n on top. So the total number of times is now n plus 2. Is that okay? So differentiating something that has already been differentiated 2 times, n times, will now make a total of n plus 2 derivative of that stuff. Then plus. Now we now come to this one. We're now going to apply the Leibniz-Maclaurin. Anytime you see a product of some function of x and some function of y, or your derivatives, you need to use the Leibniz-Maclaurin. And which one are you going to use as your u? Which one are you going to use as your v? Now, I'm going to use this one as my u because I can readily obtain the nth derivative. As a matter of fact, the nth derivative of this one will be yn plus 1. So this is my u and this is my v. So I'm going to apply that trick like this. So remember the rule, your combinatorial coefficient is 1. In the first time that you're differentiating, you now differentiate your un times, giving you yn plus 1. Then you're now going to keep your v. You're not differentiating v in the first term, okay? You don't differentiate v. Then in the second term, let me put a big bracket. You now put your second combinatorial coefficient, which is n combination 1, and that's n. Then you now differentiate this particular one, okay? Reduce the order of differentiation. So in this place, it was n plus 1. So if you differentiate it n minus 1 times, you will now get what? Yn. So n minus 1 times is 1 plus n minus 1, which cancels out what? The minus, the 1 and 1 cancels out and leaves you with n. So the way I'm going to be doing it is, I'm just going to be reducing 1 from the powers like this. Is that okay? So I've differentiated this one n minus 1 times. So after differentiating this one n minus 1 times, then you have to what? Differentiate this one 1 time, so that n minus 1 plus 1 will give you n. Remember, the power, the number of times you differentiate v plus the number of times you differentiate u in each term must add up to n. So if you differentiate x, you get 1. Now, if you're very sensitive to what I said that anytime we differentiate our x and we get a constant, there is no need to continue again because other terms will be 0. Is that okay? So this is where we're going to stop. We have successfully differentiated this term n times. Then if you go to this last term and you differentiate it n times, it has not been differentiated before. That's why I put 0 before. So 0 plus n is going to be n. So you have your n derivative equal to 0. Now you have to what? Solve this differential equation in the next step, which is what? To plug in x equal to 0. So when you put x equal to 0, what you're going to have is this term will cancel out. This term will cancel out. You just be left with yn plus 2, then plus, you just be left with nyn. Nyn times 1 is nyn, then plus what? Yn equal to 0. Are we together? So if we collect the like terms, we have yn plus 2, then plus n plus 1 all in yn equal to 0. This translates yn plus 2 to minus n plus 1 y of n, and this is called the recurrence relation in step 3. So a recurrence relation is a relation that will enable you to be able to find the coefficients of your differentials, okay, at some particular integer values of n. So n can be greater or equal to 0, meaning that we can use 0, 1, 2, 3, 4, 5, okay, and so on and so forth. So this is our recurrence relation in this case. So I want you to take note of something, that you see me as we actually crossed this point where we were to put x equal to 0. Now the nature of this thing and the interpretations, they now transformed implicitly. It's not really explicit, but it's implicit. So what am I trying to say? Immediately you solve this equation by putting x equal to 0. Yn plus 2 is actually the same thing as fn plus 2 of 0. Do you understand? That means it is this yn plus 2 that you're seeing here is actually the fn plus 2th derivative of this function at 0. Do you understand? Similarly, yn is actually the fn of 0 derivative. And similarly, anytime you see something like, if we get any other thing following, all of them are actually the derivative of this function at the point 0. So 0 is a special point. 0 is a special point when you're using power series method, okay, to solve this problem, especially the Leibniz-Maclaurin method. So anytime you see me writing yn plus 2, I actually mean what? Fn plus 2 of 0. In another book, you might see them writing something like this, yn 2 of 0, something like this. Just trying to tell you that it's actually meaning the value of the derivative, the value of the n plus 2th derivative at the point 0. So this is our recurrence relation. So let's now find different values of our derivatives at 0 using the value of n, varying the value of n. So we'll start with n equal to 0. So when n equal to 0, you're going to have y 0 plus 2 is 2 is equal to minus 0 plus 1 is 1, and 1 times y naught is still what? Y naught. Are we together? So y2 will be y naught for n equal to 0. So when n is equal to 1, you're going to have y1 plus 2 is 3 is equal to what? Okay, you now have minus 1 plus 1 is 2. Okay, that's 2. Then y, well, in 1, so y1. Is that okay? So I'm going to show you something that usually happens, but just follow me. So let's solve up to. It's usually good when you are given a problem in power series, you should stop at 5. Don't be relaxed not to stop at 5. Stop at 5. Okay, solve at least from 0 to 5 for your values of n, so that you can have enough values to convince whoever is marking your script that your answer is also on track. And if you are stopping at 5, it will help you to figure out a pattern that is actually developing in the answers that you'll be getting. If you stop at 4, you may not really see the pattern clearly, but stopping at 5 or having 5 iterations or 6 iterations helps you to discover the pattern that will be forming in your solution. Is that okay? So when you solve for n equal to 2, you have, of course, remember, I'll copy out the recurrence relation. Yn plus 2 is equal to n plus 1 minus n plus 1 yn. And remember that these things are still the same thing as yn plus 2 of 0 is still minus n plus 1 y of 0, yn of 0. Okay, but I don't want to be stressing myself to be writing bracket and 0. I just know that it is what it means. So permit me to only stick with this for now. So you have your, when n is equal to 2, when you substitute it here, you get y4. That's 2 plus 2, 4 is equal to minus. Then 2 plus 1 is a 3. Then you have your what? y2. Remember, n is 2 in this case. So when n is 3, we'll just do that quickly. We'll have our 3 plus 2 is 5 is equal to minus 3 plus 1 is 4, and you now have what? Your y3. So definitely when n is equal to 4, you're going to have your what? y6, okay, is equal to minus 5y4. Then when n is 5, finally we're going to have y5 plus 2 7 minus n plus 1, which is 5 plus 1 6y5. Okay, so let's modify our answers a little. Okay, now in this particular one, when we are solving for n equal to 0, we have y2 equal to minus y naught. Okay, so y3 is equal to minus 2y1. Now see what we get in y4. Y4 is equal to what? Minus 3y2. y2 is already defined in terms of y naught, so you can actually see minus 3 times what? Minus y naught, which gives you what? Very good. It gives you what? 3y naught. Is that okay? So you're modifying your answer. Now this one is y4 in terms of what? y5 in terms of y3. y3 is already found in terms of y1, so you have to modify it. Minus 4 and times y3 is what? Minus 2. Okay, y1. Okay, so in place of y3, you're replacing it minus 2y1. Now apart from the negative signs cancelling each other, I suggest you don't multiply. Don't tell me 4 times 2 is 8. I know 4 times 2 is 8. I'll just leave it as 2 times 4 y1. Is that okay? So we're not going to multiply, we'll leave it like this. So the essence is that you want to use it to figure out a pattern. Is that okay? So let's look at y6 in terms of y4. y4 is already evaluated to be what? 3y0. So we now have minus 5, and we now have what? 3y0, which I can write as minus 3 times 5y0. naught. Are we together? I'm not going to multiply it. Everybody knows that 3 times 5 is 15, but the essence of leaving your answer like this is so that you can figure a pattern out. So for this particular one, you'll have your y7 in terms of y5. It is minus 6 y5. What was y5? The y5 we got has now been written in terms of y1, and this is 2 times 4, okay, y1, and somebody can write somebody can write negative 2 times 4 times 6, okay, y1. So if we wanted to solve for n equal to 6, just to clear our doubts, we'll get n equal to 6 will give you 6 plus 2, 8, according to the recurrence relation, minus 6 plus 1. Where am I getting it from? 6 plus 2, 8, then minus 6 plus 1, which is a 7, and you now have your y6. Okay, see what it's going to give you. It's going to give you minus 7, and the value of y6 we got is what? Negative 3 times 5 y0. Now the pattern is minus cancelling out minus. You now have 3 times 5 times 7 y0. Now let's study the pattern. So for our y2, we have minus y0. So for our y3, you have minus 2 y0. So the 2 is odd and the 3 is even. Now on going on to the next one, I now have what? Another odd number now taking the place of y0. Every time that has y0, you discover that the odd number is coming, increasing. We started with 1 as the first odd number for y0, then 3, that's, I can write this thing as 1 times 3, okay? Then the sign also has flapped from 2 to 4. Now when we go to 6, the sign is now minus 3, and another odd number has joined. So when we go to 8, the sign has now changed from minus to positive. So there's like a flip-flop of signs happening in terms that have y0, okay, and those terms are increasingly being multiplied by the next odd number in the series. So if you look at your y, that's your terms that have y1. We started with minus 2, of course, which is still the same thing as minus 1 times 2. Then if you go to the next term in y1, you see that it has now flapped sign. It's now positive. Then 2 times 4. 4 is the next even number. Then if we go to the next term having y1, you now observe another pattern. The minus sign has now come back again. So 2 times 4 times 6. So with this, you figured out the pattern that is happening. So you can now write your solutions like this. So your solutions, our solutions is defined as y is equal to, our solutions is defined as y is equal to, we are defining it in terms of the Maclaurin solution. So the Maclaurin series solution is actually defined, if you remember, we have our y0, then you now have plus x y1, then plus x squared over 2 factorial. You have your y2 plus x 3 over 3 factorial y3, then plus x 4 over 4 factorial y5 and 4, then plus x 5 over 5 factorial, you have y5. Okay, I stopped at 8, right? So I'm going to plus x 6 over 6 factorial, you have your y6, then plus x 7 over 7 factorial, y7 plus x 8, sorry, x to the 8 over 8 factorial, and I have your what? Y8. Now, this is kind of like different from the Maclaurin series, you know, right? Yes, I understand. In the Maclaurin series, you know, this one was actually f of 0, this is your f prime of 0, and this is your f prime prime of 0, and so on, f prime 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 of 0. So this y3 is f prime prime of 0. So that's the same way I want you to see it, okay? That's the same way I want you to see it. So this, your y0, you're going to see it as f of 0. This, your y1 is f prime of 0, and so on and so forth. y4 is fiv of 0, and so on and so forth. This is vii of what? 0. That's the 8th derivative at the point 0. So why am I emphasizing at the point 0? Because if you can remember, we actually solve this particular equation by substituting 0 after we differentiated n times. So the point after which we substitute 0 now transform to this guy, to your fn plus 2 of 0. This is your f fn of 0, and this is your fn of 0. So anything you're seeing here now from this point here on after is no more, you are no more seeing it as an nth derivative, but you're actually seeing it as an nth derivative at 0. Do you get the adjective? It's not more an n derivative alone, but an n derivative at 0. Are we together? Now we're now going to substitute what we got. Y is now going to be our y0 stays the same, then our y1 actually stays the same, xy1. Then for our y2, see where it now comes to play. Our y2 is minus what? Y0. So my y2 is minus y0. So I'm going to put my minus y0, okay, over 2 factorial, then I now have what? X squared. Then let's see what y3 is. Y3 is actually expressed in terms of y1. Then you now have what? Minus 2y1. So y3 is minus 2y1. So I'm going to write minus 2y1 all over 3 factorial, then x cubed. Are we good? Then if I go to y4, what is y4? I'm tracing what y4 is. Y4 is 3y0. So instead of me to write y4, I'm going to write plus 3y0, then x to the 4 over 4 factorial, then plus, let's continue. My y5, what is my y5? My y5 is actually 2 times 4y1. Okay, then I have what? 2 times 4y1 all over 5 factorial, then x to the 5. Okay, then let's go to the next term. You can see that I'm checking the next term before I write this sign so that I won't be confused. So y6 is what? Negative 3 times 5 y0. So I have negative 3 times 5 y0 all over 6 factorial. Okay, the 6 factorial is coming from here. Then you now put x raised to the power of 6. Then let's check what y7 is. Y7 is actually negative 2 times 4 times 6 y1. So you now have what? Negative 2 times 4 times 6 y1 x to the 7, and all over you have what? 7 factorial, and plus y8. So what is our y8? Our y8 is actually what? 3 times 5 times 7 plus 3 times 5 times 7. You now have plus 3 times 5 times 7 y0, as you can see, then all over 8 factorial, since we're in the term having to do with x raised to the power of 8. Then it goes on plus dot dot dot. Now, one thing you should notice is that power series solution of solving second order differential equations, your answer is going to be expressed in terms of y0 and y1. Y0 is actually your function, your f of 0 or your y of 0. Okay, now y1 is actually your f prime of 0, or is actually your y prime of 0. Is that okay? Or the value of your derivative at the point 0, the value of the first derivative at the point 0. So that's what it means. Okay, so this is initial conditions. These are initial conditions. Y0 and y1 are initial conditions. Now whenever you solve any second order differential equation with power series, you will always get that your y0 and your y1 will be what can represent generally other terms. So the essence is this. I'll show you why we actually need to get our answer like this. So when you factor out all the terms or you collect all the terms having y0 together, we'll get our y0 brackets. So we have 1, okay, then the next term following is minus, I have 1 over 2 factorial, and I have x squared. The next term following is plus, I have 3 over 4 factorial, then I have what? X to the 4. Okay, then the next term following is minus 3 times 5 all over 6 factorial, and I have x6, and I have the next term following is plus 3 times 5 times 7 over 8 factorial, and x to the 8, then minus dot dot dot, whatever the pattern is continuing. Okay, so this is all the terms in y0, then plus we're going to collect all the terms in y1. So y1 into what? So all the terms in y1, the first term is x. So when you factor it out, you get x. Then is it plus or minus? That is the next one. Then the next one is a minus. So I have a minus. I'm factoring out y1. You'll be left with 2 over 3 factorial x cubed. You now have minus 2 over 3 factorial x cubed. Then the next term in y1 is this guy over here. You have a plus sign, 2 times 4 over 5 factorial. So you have plus 2 times 4 over 5 factorial x5. I can guess the next term it will be minus 2 times 4 times 6 all over what? Very good. 7 factorial, then x to the 7, as you can see over here. Then plus dot dot dot. So this is how it goes. Now this can be written as y is equal to, you can call it an a. This whole series can be written as, let me say, your g of x, and plus this one can be written as b. You can write this one as h of x. Do you understand? So remember that anytime we have a differential equation, okay, where we have two arbitrary constants, what happens? We need to differentiate 2 times. So in this case, a is standing for y naught, that's my y naught, or I can call it my f of 0, and b is standing as my y1, okay, which is my f prime of 0, or y1 of 0. Okay, so this is the concept of solving second order differential equations with power series. You always get 2 arbitrary constants, and the 2 arbitrary constants are your y0 and your y1 of 0, those initial conditions, okay, at the point when x equal to 0. So sometimes they may not always be 0, but we are just using 0 as a reference point, okay, for starting. So this is the solution of this differential equation, and this is how you address it. So I know this video was quite long, but we're going to go to the next problem, and when we solve the next problem, I believe your understanding in power series will be solidified for life. So don't forget to like, please. I need your likes, very important. Subscribe, hit the notification bell to stay updated, and good luck with your exams. Bye till next video.